I'm a PhD student in chemistry here at Caltech, and I have a subject minor in environmental science and engineering. And broadly, what my PhD is about is renewable energy storage. So we love wind and solar, but wind and solar are variable, and it's hard to get to 100% reliability with wind and solar alone. So you need to pair wind and solar with energy storage. One example of energy storage is batteries. Batteries are great, but sometimes they're very expensive. And so I work on something called hydrogen fuel for energy storage on the seasonal grid scales. So we're talking about a lot of energy for a whole country for a whole season. And hydrogen is maybe better for that. And batteries are maybe better for the daily storage needs. So I look at the complementary roles of batteries and hydrogen for renewable energy storage. And then in the lab, I also am trying to develop catalysts which make the hydrogen. So I'm trying to make the production of hydrogen fuel for storage cheaper by making better catalysts that are active, efficient, earth abundant in the lab. Yeah, so I have kind of a half and half lab. Yeah.
I think. Oh, sorry. I think we'll let all the panelists give a short introduction, and then we'll open it up to questions.
Thanks for your question.
But thank you. Yeah, we'll come back.
Right. Hey, everyone. My name is Shreyas Visapragada. I am a third-year PhD student in the Planetary Sciences Department at Caltech. So my research broadly is focused on understanding the formation and evolution of planetary systems, both our solar system and systems outside our solar system, extrasolar planets, which are my two words that you can no longer see. So to give you a little bit of a taste of something I'm currently working on, I am interested in how the atmospheres of planets can evolve. And in particular, right now I'm thinking about extrasolar planets that are really close to their host stars, their suns, and in receiving so much radiation, their atmospheres evolve way differently than our Earth's atmosphere may have evolved. And so I'm trying to think about ways to see those changes and understand how exactly planetary atmospheres respond to radiation.
Hi, everyone. My name is Phil Jahelka. I'm a grad student in applied physics working on low-cost solar cells. And so the motivation for my research is that solar cells, as they are right now, are already the cheapest source of electricity in terms of dollars per watts. And what's really holding them back from taking over the world at this point is the enormous capital cost that goes into turning sand into a semiconductor, which is this extremely high purity, chemically engineered product. And so what I'm interested in is how do you use these very high purity, high capital cost products like silicon or gallium arsenide very judiciously, and then use very low cost processing to make a low capital cost, good enough solar cell that manufacturing can expand very rapidly to meet the demands of mitigating global warming.
Hello, everybody. My name is Newton Nguyen. I am a third-year student in environmental science and engineering here at Caltech. I also have some slides back here. So what I broadly work on is essentially there's some telescopes outside, and if you turn them around, you can see the Earth in a pretty high definition instead of those 16 pixels you saw earlier. First slide, please. Yes. Thanks. So what we see here is a map of methane emissions, methane concentrations taken from our European friends at the European Space Agency. And what we could do is we could actually map the entire globe of and look at the methane, the distribution of methane around the world. Methane is the second most important greenhouse gas. It's responsible for about 30% of climate change. And you kind of see over LA, there's a pretty big methane plume there. I wonder why. And you can see over the East Coast is quite a big concentration of methane there as well. So what we work on in my lab is understanding how does carbon cycle through the atmosphere of the Earth. And another important aspect of that is understanding how plants uptake carbon because plants do photosynthesis. Next slide, please. So when plants are producing, when they're taking up CO2, when they're making sugars, when they're doing photosynthesis, what they're doing is they're actually glowing as well. But you cannot see that with the naked eye. So what we call that is solar-induced fluorescence. And what we see here is a map over the United States of this photosynthesis solar-induced fluorescence, so this SIF, as I'm going to call it for the rest of this talk, is in fact a proxy for photosynthesis and carbon uptake in the atmosphere and in the biosphere. Could you press the next button? So this is a video of photosynthesis and SIF over the last year. So this data is actually just published about 2 weeks ago. And what we see here is the seasonal cycle of the United States. And you could kind of see in the Midwest, as spring starts occurring, the corn gets planted, and the production of plants just increase dramatically. So, specifically like you also have soy and those other plants. They're very big carbon sinks. So they're extremely optimized to take up carbon and produce sugars. Yes, but so I will be talking about this and climate change and how we could observe climate change from space. Thank you.
All right. So now let's start taking questions. And I'll walk around with this microphone so that you have if you ask your question in the mic, then everyone can hear. Do you want to ask your question? Yes.
So about solar cells, I have read that there's a shortage of sand in the sense that sand is used to make concrete, and there are implications in terms of as we build out and develop more and more of the world that we could get to the point where we're running out of sand. Does that complicate or compromise the ability to make solar cells, or are the alternatives that you're talking about potentially a solution to that problem? I know it seems sort of ridiculous to think that we could run out of sand given how much there would seem to be, but that's my understanding.
Yeah, thank you for the question. So I'm not an expert on making concrete. It's something I'm interested in because my understanding is that producing concrete is about 10% of global CO2 emissions. And I have also heard this thing about us running out of sand. And what I've heard is that not all sand is created equal. Like, not sand, there isn't just one kind of sand. And so there's like certain sands in particular from like riverbeds that have like a very nice microstructure for structural properties for concrete. Whereas the sand that goes into making silicon just needs to be reasonably chemically pure. And as far as I know, there's not any shortage of sufficiently pure sand, and part of turning sand into silicon anyways is going through a number of chemical purification steps. We don't really care about the granular structure of the sand like you do when producing concrete.
So something really exciting, someone who was a PhD student at Caltech is now doing their postdoc at Berkeley. His name is Cody Finke. He has a startup that is based on renewable cement. So basically he's making the same exact chemical that is in all of these buildings that hold us up. But when you typically make cement, you emit CO2. But he's doing it differently, where he emits a different chemical and then captures it. And so it's really exciting, and he has $1 million invested in his company already. And so I'm optimistic about this. So definitely green cement. Cement is one of the most, cement, steel, and long-distance shipping are some of the most difficult parts of our energy system to decarbonize. And so I'm very excited about his startup for decarbonizing cement, because that's really important and hard to get out the CO2 in our energy system.
If you ask it in the mic, then it'll.
Yeah.
So, with what you said,
Yeah.
can we recycle the
That's a good
cement?
question.
Like when
Yeah.
we tear down a building, can we recapture what we spent?
Yeah, that's a good question. I don't actually know that much about material recycling with the cement, but I know that it's not just about tearing down buildings. I think the rate of us growing, and we're predicted to build a lot more buildings than we are tear them down. So if we want to have a 100% renewable renewable economy, then somehow we still have to figure out how to get the CO2 out of cement. And something that's really exciting is that places like California have laws on the books that say we have to have 100% of our electricity come from net zero carbon emissions sources by 2045. And lots of different states are actually copying California and are doing this so I think Nevada has passed a law, Nevada, Washington, Hawaii, Puerto Rico, New York, and Virginia. It's going through and New Mexico. Virginia, they're voting on it right now. So there's a lot of reason to be optimistic about sustainability, especially on the state level. Yeah. Thank you. Yeah. Thank you. Yeah.
Do you have a question?
Yes, my name is David. I'm a nascent citizen scientist. So I would like to know, because I've been looking at this show called Curiosity Streaming, can you give me some information on hematite? Which is
I know a tiny little bit about hematite. Do you have any specific questions about the material? Like, I know it's
the only thing that I heard is like the holy grail of this world. So I don't.
Do you mean like specifically in reference to making like cheap solar
iron.
cells?
It's iron.
Yeah. So there are a number of interesting materials, iron-based in particular, that seems like they should be able to make good solar cells. The two that I've heard of are particularly hematite and pyrite, or fool's gold. Both of them have good optical properties for making solar cells. The issue is getting the sufficient purity you need to make a solar cell out of that material. So in order to make a good silicon solar cell, you need material purity on the order of like 1 part per trillion impurities in your material. And that no one's ever been able to figure out how to pull this off with iron sulfide or iron oxide, just due to the chemistry of those molecules, whereas we have good ways for making extremely high purity silicon that you can use for making devices. I don't know. I would need to know more details about specific proposed technology. Like, it's a great idea for solar cells. We just don't know how to make it in a high enough grade to use it for that purpose. Thanks for the question.
Hi, Jackie. You were mentioning about hydrogen energy. I don't know if that's energy storage. I don't know much about any of this. But every time I hear about hydrogen, like hydrogen cars, hydrogen, that's water vapor, that water is used for the energy, correct? Yeah. And that means that water vapor is released into the atmosphere. What does that do to the environment that doesn't have so much water, humidity in the air when we're bringing in, when we stand next to a golf course, we know golf course, right, where they water. We know that the humidity, the entire atmosphere is changed. It's different than just a few blocks away. What does hydrogen really do? Because we know that everything has a consequence, no matter what we do. So can you talk about it a little bit, how hydrogen would change the atmosphere, or any of you?
Yeah, so So first of all, that's a good point. Whenever you talk about new devices, you have to think about what's going to happen. So that's a really good way to be thinking about new devices. So what my work shows is that hydrogen, it's not necessarily best for use in cars, but more use in like a large-scale central plant. And so exactly what you said, it comes from water. You take water, you split it into two. You have hydrogen and oxygen, and then you use the hydrogen as a fuel. So you can stick it in a can like or a tank like gasoline, so that you can use it whenever you want. And then when you use the hydrogen recombines with oxygen, and you get water back out. And so in this way, the water is it's a closed loop. So the water is never going anywhere else. You use the water to make hydrogen, then you let it come back together when you want to, and then you get the water back again. So you're actually not letting the water go anywhere else than in your one hydrogen storage central plant. Yeah. So that's a great question, though. Yeah.
Do you have a question?
Jackie?
Yeah.
I think you mentioned before, you said
Wait, can you talk a little louder? Sorry.
Hello?
Yeah.
Okay, you can hear me?
Yeah.
You mentioned before that there was a grad student here who moved to Berkeley to be a postdoc and as a
Wait,
startup.
sorry. Oh, yeah, yeah.
So you said that from buildings you emit CO2, and instead when he builds cement, he emits a different chemical. What is that chemical, and what does he use with it?
Yeah, so this is actually proprietary information because that's his way of that's how he's gonna make money.
I get it.
So I can talk to you more after.
Yeah, sure.
Yeah. Yeah. But that is the money question. So.
I get it. And Shreyas, I had a question for you.
Yeah.
So you said you study how extrasolar planets form. What information or data do you use?
Yeah, so there's two ways you can go about it. One is that you can see all of the extrasolar planets that we have now, and based on sort of the population of planets that we see, try to infer what must have happened to these planets to see what we see today. And the other, which is a really incredible and new direction that this field has taken over the past maybe 10 to 15 years, is that you can image directly the cradles of planet formation. So there are telescopes, specifically one array of telescopes called ALMA, and the ALMA array is really, really sensitive to the cradles of planet formation, basically the disks of gas and dust from which planets are born. And both ways are really interesting and useful ways to put constraints on how planetary formation actually occurs. Great question.
More on the exoplanet stuff. Earth has a magnetic field around it. How many other planets in the known universe have magnetic fields? Oh,
phenomenal question. I have no idea. That's how you know it's a good question, right? It is absolutely, I think, an open question. We know a fair bit about the mechanisms that can generate magnetic fields, but they are notoriously difficult to observe. Even in our own solar system, the sort of geometry of Uranus and Neptune's magnetic fields are actually really, really tough to pin down. So that's not even getting beyond our solar system, right? So figuring out the magnetic fields of things like hot Jupiters and planets orbiting other stars is a tough thing to do. But there's people actually here working on it using radio telescopes. There's a guy named Greg Hallinan, I believe, who's very interested in this question.
So this is related to a couple of questions ago about silicon purification. Is there a better way to purify silicon than going through silicon tetrafluoride?
Sorry, I missed the last part of the question.
Is silicon tetrafluoride still involved in the purification of silicon for solar cells?
Yeah. So for those who don't know, here's how you turn sand into silicon. what you do is you take a bunch of sand and you put it in a graphite arc furnace at 2,000 degrees C with some wood and coal. And what happens is the wood and coal burns the oxygen out of the sand, and you're left with metallic, metallurgical grade silicon. You then take that silicon and react it at a very high temperature with hydrochloric acid to form trichlorosilane, which is this horribly reactive, toxic gas. And then you flow that trichlorosilane, which is now pretty high purity, through these high temperature chemical reactors about the size of this room, where they get the interior of the room extremely hot. The trichlorosilane, because it's so hot, breaks down and deposits silicon on the inside of this room. You then scrape the silicon from the inside of the reactor and melt it back down and recrystallize it, and now you have semiconductor grade silicon. So the overall process is you're starting with a rock that is sand, you're vaporizing it and recondensing it into another rock, which is your metallurgical grade silicon. You're then vaporizing that rock back into a gas, which is the trichlorosilane, breaking that gas back down into a rock, melting that rock, and re-solidifying it. And now you finally have your starting material for like doing all the device fabrication. And this is just like wildly expensive to do, but it works surprisingly well. And as far as I know, this is the process that was established really back in the 60s for making high-grade silicon, and it hasn't really changed a lot since then. There have been other techniques, in particular like a buzzword that was flowing around for a while was upgraded metallurgical grade silicon. And the issue is that you just can't make pure enough material to do the job using these sorts of techniques. But yeah, thanks for the question. I mean, it's something people have been working on for a very long time, and as far as I know, there's no compelling improvements to the process.
So when this is such a long way to go, how good are you in recycling solar cells to get back the silicon to maybe go over many life cycles of the molecules to like reuse them? Would it cut the costs a lot over the cycles? Can you do this?
Maybe in the distant future, but not right now. And there are a couple reasons for that. First of all, the lifetime of a silicon solar panel, like just sitting out in a field, is about 30 years. And so it's 30 years of installation before you have to think about recycling that panel. In addition, right now, solar photovoltaics only make up about 1% of U.S. energy production. And so we want to grow that by a factor of 100 to, have 100% energy production, and more like a factor of 300 for like being all of the U.S.'s energy needs. And so it's going to be a very long time of making brand new solar panels to hit those energy targets before recycling becomes something we have to really think about in a big way.
So one of the JPL von Karman lectures last year was focused on the observations and data that we get from climate, satellites that are focused on Earth that look at cloud cover and temperature and all the other data that they can measure. And my takeaway walking out of that presentation was, these are not the words of the presenter, but my takeaway was we're screwed because there's not a lot of political will to do drastic things to reverse these trends. And so it seems to me like in order to create political will, many, many disasters are going to have to happen. So I guess I want you to tell me why I'm wrong and like tell me what your optimistic visions are for how we slow and mitigate climate change. Will it happen through technological advances, electrification, solar and renewable energy, or are there some other things that we haven't even really gotten off the drawing board yet that are going to revolutionize the future and allow the climate to be habitable?
Wow, you asked a very existential question. But I guess I'll kind of lay out the data first. So essentially, the largest uncertainty in climate change projections is the physical uncertainty is clouds. But the but by far the largest uncertainty in climate change projections is how humans will change, or how humans will respond to climate change. For example, in 2050, what are our CO2 emissions and methane emissions going to be? So, so the question then becomes, all right, so what are like very possible pathways for us to mitigate climate change? And the United Nations pointed out that it would be the fastest way to actually cut climate change would, or to buy us more time, would be to cut methane emissions. And that comes from just having stricter regulations on fossil fuel production. For example, like flaring of methane in the when doing the wells, as well as like having tighter security around pipelines. That's like one thing. Yeah, and but another pathway would be to is through geoengineering, and that's an active area of development. Like speaking from my own personal perspective, climate change is a pretty big issue, obviously, and you need to have this kind of world unity to actually tackle this problem. The problem is, the hard part is that like policymakers have known what to do since the 1990s. The first climate change report came out in 1990. The question is, how do we get action? But there has been previously action on an international scale for climate. Did anybody here remember the ozone hole? That was an international agreement, and every country signed up for that one. And we now see, our data now shows from the satellites that the ozone hole is recovering. So, sorry, excuse me? Mm-hmm. Mm-hmm. Mm-hmm.
Yeah, so part of my work is on macro energy systems, which touches on a lot of what you're saying. This is a big, we're talking about big geographic scales, multiple decades of transition period, multiple countries. There's a lot of things at play. So going back, you were saying, tell me why I'm wrong to be cynical. I just want to repeat about the state laws, especially California. It's on the books law that by year 2045, all of electricity in California will be zero carbon sources. That's amazing. And there's like 7 more states that have these laws on the books, and it's just more states are thinking about it and considering these policies. So that's a reason to be optimistic, especially on the state level. But yes, how are we going to get there? That's also a really hard question. So yeah, and then I guess you're so there's transportation, there's heating, there's the electricity sector, and there's also aviation, which requires very energy dense fuels, and there's cement, like how we talked about before. So exactly what Newton said, we do have to like work together to figure all this out. And then the other thing you talked about with the developing countries, something that 2 of my advisors just had a big conference with to try to ask this question what about the developing countries, and what they actually found is that the CO2 emitted per person in a lot of these developing countries is so much smaller than the CO2 emitted per person in countries like the US, that their conclusion from this meeting with the top experts, is that let them develop. And actually, when you develop, when you're richer, then you emit less CO2 and your population grows less fast. So their answer was, it doesn't matter what the poor people of the earth do, let them develop, and really we have to curb our CO2 emissions, was their conclusion from this big meeting. And so, yeah, there's a lot of moving parts. You basically, what you're talking about right now is the field of macro energy systems. And so I would encourage you to Google and read some of the papers under that keyword. So, yeah.
And also, as just what Jackie said about the population, like if we take the average American and multiply it by the number of people, like let's say you take the carbon consumptions of the average American and you multiply it times the population of the Earth, then that would actually take up as many resources as 5 Earths. So there's like a vast disproportionate amount of carbon emitted by, let's say, rich countries than there is to developing countries. But there's, I think that there needs to be an economic incentive for people for like countries and for companies to start mitigating climate change. And a part of what we do in my lab is we try to figure out exactly where the carbon is coming from. So then that could be better regulated, but also so for example, we could detect methane leaks from space, and that not only prevents like climate change, but it also saves oil companies money. So how do we get these incentives to align? And we need to make those incentives, we need to make a policy structure such that these incentives align. And that's what's going on right now.
So I agree with Jackie Newton that there are encouraging things, but I broadly agree with the von Karman lecture guy that we're hosed. Oh, that was your takeaway. Well, so something I've been really interested in is looking at like the economics of how industries grow. In particular, like how do you turn profit into improved production capacity? And there's been a couple really interesting papers about this, specifically for solar cells and renewable energy over the past 3 or 4 years or so. And like these economic papers have really strongly affected my view on like what I think is interesting to like do research on, and sort of what I and like other people in my field have come up with is that if you want to decarbonize the economy, you're looking at about $30 trillion of capital investment over the next 40 years or so. And there is just like no serious policy proposals to dump that kind of money into renewable energies. And so like sort of the two ways forward are either figure out how to make ultra low capital cost devices and technologies, or very large scale political agitation. Those are sort of the two options that I see.
So you showed the plot of the SIF, and you showed that the Midwest has photosynthesis going on. But most of that photosynthesis is for the corn itself, the plant, which then gets plowed back under. That's not actually pulling out any carbon, is it? It's just cycling the carbon.
Yeah, so part of the carbon, most of the carbon is being recycled back into the atmosphere because you have the microbes respirating. Basically, they're decomposing the carbon from the plants. But you do have also like some better farming practices that could contribute to just burying the carbon and just leaving it in the earth forever, essentially. Oh, sorry. Could you hear me now? Or were you able to hear me before? Yeah. So it definitely depends on the the farming practices there. But yeah, that is a very good point. And you could definitely carbon burial is a geoengineering technique that is being researched. Yeah.
Just a quick reminder, the telescopes are available outside for whenever you want, but we will keep the panel going until at least 8:30. Yeah, you can go out to the telescope, come back to the panel.
Another question, probably for Phil. You were mentioning that you're working on the solar cells, that they're cheaper and more, that we can produce more. Has there been sorry, losing my thought or my tongue. Is there another way to make solar cells or something similar with reusable, with recyclable materials, glass that is already, or concrete that is, as opposed to the traditional way where we're mining mountains? Yeah, I guess that's the question.
Yeah, so you can definitely make a lot of a solar cell out of recycled materials. So the two probably most important materials in making a solar panel that aren't the silicon are aluminum and glass, which are already like two of the most recycled materials on the planet. And so recycling that seems extremely feasible, along with recycling the silicon itself. The issue is that we need to make an enormous number of new solar panels in the first place. And so there's not a lot of value in recycling existing solar panels when we need to make 100 times more than we already have right now anyways. Sorry, does that address your question?
Maybe you go ahead.
For Jackie, so you're in the renewable energy storage world, other than hydrogen. What else have we got?
Yeah, so great question. We have batteries. We have pumped hydro storage. We have compressed air. There's not that much that's good for seasonal energy storage, and that's kind of the money question. Batteries tend to fill this niche that is like smaller scale, so batteries are great for your phone, maybe good for your car, great for your laptop, maybe good for like 12 hours of storage to offset the solar cycle so you can have energy at night when the sun is down. But we have big seasonal cycles in our wind and solar variability. So in the summer, the wind in the US goes to big lows for like multiple weeks. And so that's kind of the hardest part in the energy storage world, is how to fill this seasonal storage gap. So we have the things basically, hydro, pumped hydro, which means it's like a water tower, but then hydro is like a dam, and then compressed air is squishing it and letting it go, and then there's also, geothermal is really exciting. So actually in my undergrad in Minnesota at Carleton College, they installed geothermal heat pumps underneath all the parks, and that caused them to reduce their CO2 emissions by a third, 30 to 40%. It was amazing. So how that works is basically the ground is always a better temperature than it is in the air. So in the winter in Minnesota, it's really cold, but the ground is a little bit warmer. So you can take your cold water and then make it a little warmer. And then in the summer, the air is always hotter than the ground, so you can take your hot air and hot water and make it a little colder. And they do this kind of water cycling heat pump with geothermal, and that helps their seasonal energy storage problem. So it's a really great question. If you have an only wind and solar based electricity system, which is kind of what these state laws are tending toward, where they're kind of retiring a lot of their nuclear plants, and they're saying it has to be zero carbon resources for the electricity. It kind of, if you only have wind and solar, you really have to work on dealing with the seasonal variability. So yeah, that's a great question. Yeah, but I'm really excited about geothermal in addition to hydrogen because it worked on my school. So yeah.
I in fact have two questions. So one, just basically it was the same question. So how it is with methane then? Can you compared to hydrogen?
Wait, methane. Oh, yeah.
Methane, yeah, because we have a distribution system already. It's not as explosive. We can catalyze it. We can store it way better. It's less dangerous.
Yeah.
So why isn't it favorable over hydrogen?
Yeah. So so it's really exciting. We work with SoCalGas, the Southern California Gas Company, actually, so methane, basically, when you burn it, you still emit CO2. So. And if we're going to be in these laws in California, which is on the books in 2045, we can't be emitting CO2. So if you are using methane, then you have to pay to capture the CO2 right when you emit it. So carbon capture and storage is another technology that people are using, where you have a power plant, you emit CO2, and then you capture it, and then you put it underground, basically. And the problem with carbon capture and storage is that the way the law is written now is it has to be 100% CO2 free, and carbon capture and storage isn't 100% efficient. So you're going to get little bits of CO2 off the end. And so maybe they'll change the way the law is written, but currently the way the law is written is it excludes CO2. But in the transition phase, methane is great. And SoCalGas is excited about mixing little bits of hydrogen into their existing pipelines, and mixing hydrogen in their existing turbines to clean up their existing infrastructure. So that's why they were really excited about my work, was because they can use their infrastructure to get more renewable. Yeah.
Oh, just a brief comment about methane. So when you use methane, you'll inevitably get leaks. And the thing is that methane, pound per pound, is 80 times stronger than CO2 as a greenhouse gas in a 20-year period. And it also takes quite a bit of energy to extract the methane. So it's definitely like a very good way to get. It's a very dense energy source, but it is there is also environmental costs to it as well. Thanks.
I understand that it might not be your field of expertise, but what do you think about nuclear fusion? And is it a good renewable source of energy? Is it considered, studied?
So I can't comment too much on the details of nuclear fusion, but I feel like it has been historically badly underfunded as a technology venture. I think like back in the 70s, the Atomic Energy Commission, or whatever they were calling themselves at their time, created a plot or an estimate of how much money do you have to spend over time to achieve commercial nuclear fusion by some deadline. And so they had like these like 4 different lines of like, maximum sustained effort, moderate effort, current policy, and then like fusion never was their line, was like the final line. And we've been spending below fusion never on fusion research since the mid 70s. So my suspicion is that like we can make it work. We just aren't spending anywhere near enough money to do so.
Just to clarify for other people, what we have today is fission, right? Nuclear fission. And what people are really excited about in the future, and they think, is one of these magic X technologies that could work in the law and then save all of our problems, is fusion, which is different than fission, what we have today. But a lot of people joke that it's always been 10 years away and it'll forever be 10 years away. So, but that's probably because it didn't get the money that other people did. So, yeah, just to clarify the difference. We have nuclear vision right now. Yeah. Yeah, maybe that's it. That's an astronomy question. It's the sun.
I guess if you go all the way back.
So I know that y'all are saying that methane isn't that great, but what about landfills? Like, we generate trash anyways, and that trash, it generates methane as it's exposed to UV. So California law means that we have to cap landfills, and it captures that methane, and they burn them off at landfill power plants.
I guess just to clarify the law, it's only talking about how you get electricity. It's not talking about a full economy. So they have to get rid of the methane and the waste, which is separate from getting rid of the electricity. So
yeah, they don't have to burn off the methane to generate electricity, but it's free electricity anyways.
Oh, I see. Yeah.
They have to cap it, and they have to do something with the methane.
Methane, at least methane from landfills, doesn't really actually won't produce that much energy for the amount of effort you put into actually harnessing it. So
yeah, it's like 70% methane concentration.
Sorry?
It's the gas in a working landfill up to like 7 years after it generates methane at concentrations of like 70%.
Yeah, I think it's great for like a carbon mitigation pathway to like mitigate climate change, but and it's also a pretty good avenue of getting electricity, but it's not going to fulfill all of like your electricity needs. For example, it's like relative numbers here. So the total amount of methane emissions globally is 550 teragrams, and the total amount of CO2 emissions, and that's like from combustion, would be 10,000 teragrams, right? So it's 1/20 difference. So you're going to need a lot more methane, a lot more trash to really. Yeah. Yeah, there's definitely like ways to make it. Yeah, absolutely. There's definitely ways to. Yeah.
Yeah, that's a really good point, that basically we have to think about all parts of our energy system and take the free energy where you have it, like what you're saying, free energy where you have it, but then if you really have to capture the carbon then, so pay for carbon capture and storage, and then be able to make sure that that's as efficient as possible. So, yeah. Oh, cool. Oh, wow. Right. Interesting. Interesting. That's cool to know. Cool.
So just as the resident pessimist, Jackie said something a couple minutes ago that reminded me of something that I did find optimistic. So this isn't really a question; it's just an observation that you reminded me of. A couple of years ago, I read about how there is a museum of coal in Kentucky, of course, and like 2 years ago, 3 years ago, they converted to solar power. And the head of the Kentucky Coal Museum was asked why they did this, and he said, "Well, it's just more efficient and cheaper." So I thought, well, that's encouraging.
That's cool. That's great. Yeah, I think like it also makes me really excited when we talk to SoCal Gas, because they're the oil and gas people are the ones who understand the subsurface of our Earth and the geology and how to do the engineering and deal with gas flows. And so if we can take these same people and give them new jobs with the same skills but in renewable energy, working with hydrogen fuel or working to store CO2 underground, that's the same thing. They're using engineering and geology to store a gas underground. If you can just pivot these same people to renewable energy, that's beautiful, so yeah.
So given the sad state of our climate, for Earthlings, is there like an exoplanet in our future?
No. It's really, really, really hard to get there. Point A. Getting to another star system is well outside our current technological capabilities. And point B, habitability is a really, really, really tricky thing. This is something I think about all the time when folks like Elon Musk say, like, oh, like, let's just nuke Mars and make it habitable, right? Like, we have a very, very finely tuned system on the Earth in terms of being just the right temperature to be habitable for us, just the right climate, just the right, just the right everything. And if we can't do our job here, what is the insurance that we can do it on Mars or an exoplanet or something like that? I don't know. It's pretty tough for me to see.
Hi, everyone. I have a question. Probably, I think all of you could jump in on this. Phil had mentioned earlier the economics of using or solar power being very cheap, and there not being sufficient political will. But on the flip side, fusion is very far away. Fission technology is very well understood, but it's carbon neutral, but also carries certain environmental risks. Is there anything against it economically that could prevent it from being used as a stopgap measure until the political will or the economics line up for things like solar power to take over?
I use a macro electricity system, and I plug in different technologies and see how they do, and it solves for the least cost system, and it tells me which thing competed with what and which one won and what the total system cost was. Basically, bottom line is that nuclear alone is cheaper than a solar plus battery system. But that's not really looking at the whole picture because, Do you want to talk more about nuclear? I don't know. It's kind of
I like nuclear. I think modern reactors, as far as I know, are incredibly safe. Like, one of my favorite, like, sort of little facts is that coal plants emit more nuclear than nuclear plants do. Coal plants emit more radiation than nuclear plants do like heavy metals in coal. The issue, again, is capital cost, where for solar panels, you're just putting these things out in a field and they're just chilling for 30 years. Whereas a nuclear plant is this incredibly complicated piece of equipment that if you don't treat it well, you can have very bad consequences. Whereas if you treat a solar panel badly, the worst it'll do is start a grass fire. And so looking at it both in terms of like political will and economics and potential consequences, it's hard to see fission making a huge comeback in the next 15 years or so. That's at least just my vaguely educated opinion. I can't say for sure.
I was just wondering, given the trillions of dollars of investment needed to kind of turn the tide that was mentioned specifically like in the solar discussion, how much opportunity is there for kind of the private sector, like, companies like Tesla that are developing, like energy, efficient stations for electric vehicles and that kind of thing? How does that factor into these trillions of dollars of investment needed? Because I'm assuming that's kind of more from a public sector standpoint. So how do you kind of balance the public sector and private sector point of view there?
Oh, so that number, that's purely private sector spending. So that's like people spending money on solar cells, the profit made on those solar cells going to like building new polysilicon factories. The private market can't cut it as it is right now. It's this deep irony that solar cells are too cheap is the problem. Like, if you could sell your solar cells for more money, then you could invest more capital from each solar cell you sell. But because the market for solar cells is already large, there's a race to the bottom in cell prices, and fossil fuels set a price ceiling. And so private markets cannot efficiently generate the capital needed to deal with global warming. And I think it does have to be some kind of large public expenditure of just building a large number of polysilicon plants to make solar cells. That's sort of what I imagine.
Just to be clear, you got to have storage too.
Yes.
I need a little bit help for argumentation. So let's assume I run into a discussion with one of these guys from this YouTube university that always like argue that this little smidge of carbon dioxide in the atmosphere doesn't really can do much harm. How would you go into such a discussion when, I mean, I guess you know how those people always argue, you know, this kind of flat earth line of argumentation. So what would you answer to such person that just tell you this little amount of carbon dioxide has always have been around and this increase is just a couple of ppms? They do not look about percentage. So how would you answer to those people in the discussion?
Okay.
I think this is maybe a great question for each of the panelists to give an answer to.
Oh, okay. So just starting from just the basics, I would say, so we've seen unprecedented amount of warming in the lower atmosphere. Another big symptom of carbon dioxide-induced climate change is the upper atmosphere cools down, actually. So we see a cooling in the upper atmosphere, a warming in the lower atmosphere. Also, carbon comes in different flavors. We had different weights, different isotopes for carbon. And what we've seen is a carbon-like composition of the atmosphere that has just like dramatically changed towards fossil fuel from carbon, essentially. So fossil fuel-based carbon. So just based off the weight of the carbon, based off the warming of the lower atmosphere, the cooling of the upper atmosphere, then you have climate change. If you have, like, let's say solar cycles, which is some people would say, then you'll have more of a uniform warming in the atmosphere. So that's the way I would argue that. Yeah, good question.
Yeah, yeah. Yeah. Nice. Oh, that's a good one. Yeah. Right. So I just want to tell a little anecdote about my grandpa, who's 99. So my grandpa is 99 years old, and my aunt and uncle live right next to him, and they take care of him every day. And my aunt and uncle are famous climate scientists, actually. They are both professors in the climate science world. And my grandpa was reading a lot of weird news. And basically sometimes, sometimes older people are more susceptible to fake news online. And so it was a difficult time for my aunt and uncle, who have built their whole career on climate science. And so then they stopped, they basically stopped arguing with my grandpa because they didn't want to talk about it. They thought he was crazy, they thought he was old, and they just gave up. But I was like, okay, I'm going to try. I'm going to try and convince my grandpa, who I know is really smart because he was a Berkeley PhD in chemistry. He was a professor at University of Colorado. I'm like, he can hang. I'm gonna try. I think that basically the key difference between my aunt and uncle and me was that the first thing I did when I sat down with my grandpa was I listened to him. So I listened to his astrology websites, like the horoscopes, and so I listened to all of this first. I sat down, I smiled, I listened to him. I didn't say, you're crazy, you're wrong. First I listened, and then I took him to this amazing website called climateskeptic.com or skepticalscience.com. I can't remember. Skepticalscience.com. Yeah, it's amazing. And so basically this website lays out the most common climate skeptic arguments and then really simple responses to each of these. So you don't have to be a climate scientist or an expert to know how to talk to a climate skeptic. You just first listen, smile, say, you're a human, I'm listening to you, and then just slowly ask them what do they think is wrong with climate science, and then go to whichever argument they have on the website and then walk them through the answer. And my grandpa was really getting into it, he was like, yeah, and then all of his chemistry was coming back, his geology was coming back, and then I told him that I'm working on renewable energy storage, and he said, Jackie, that's a good career. I'm proud of you. And I was it was a really, really important day for me, so I think listening first is really the most important thing when talking to climate skeptics. Right. Yeah. Yeah.
Sure. I just want to address someone in the audience. Someone over here said, show them a picture of Venus. Phenomenal answer to that question. I think Venus is a great example, particularly because it highlights that climate is such a non-linear problem. There's all these sort of tipping points and feedbacks that you have to consider, and Venus is, the same size as Earth, the same radius as Earth. If you ask an exoplanet scientist when you see a planet that looks like Venus around another star, they'll tell you it's potentially habitable, but from looking at Venus, we know that that's not always the case. I think it's really important to keep in mind the example of Venus as a case where climate goes wrong, in a sense.
Yeah, sort of an interesting experience I had along these lines was myself a couple years ago when I realized that if I wanted to be honest about fighting climate change, I was going to have to tell people that we need to spend $40 trillion, and that if I was going to do that, I should probably feel pretty good about the science behind climate change. And so for about a month, what I did was become a climate skeptic and go through and really try to understand it from a physics perspective. How does climate change and global warming work? And it ended up taking about 20 pages of physics and ending up with this gnarly integral-differential equation that I had to solve numerically to convince myself that global warming was real and made physics sense. And so if you need to start at that sort of level, it's sort of like a non-trivial thing. Another interesting thing that's been researched in psychology recently is how deeply do people hold pseudoscientific beliefs. And it turns out that for things like irrational denial of global warming or being against vaccination, both of those beliefs exist at the level of religion. And so unless you know how to proselytize really well and have those deep personal relationships that you can leverage to get people to trust you and change their worldview, it is a remarkably difficult thing to do. And if you're going to commit to that sort of thing, I think Jackie absolutely has the right answer and model in terms of how to go about doing it.
I wanted to add to that. So I have a friend who had that question exactly. Why does a small amount of CO2 do this? So I went to Skeptical Science, and I also took a course that was made by these people who made the Skeptical Science website. The course is on edX. It's free. It's called Denial 101. It's amazing. It only took an hour of my week for a month. But yeah, I know the answer to your question, which is it's just a question of balance. Only a little push if you're on a tightrope can make you fall, even if your body weight is much larger than the force that was pushed. I don't know how that makes sense, but it's a little amount of CO2 can basically tip the scales.
Question back here. Is there someone back here who had a question?
I just wanted to add to that because to me it always seemed like it's not a question of a small amount of CO2, that it always has been to me this just sort of very common sense. If we, for 150 years, we've been dumping fossil fuel, burning fossil fuels and dumping them into the atmosphere in large amounts, and it's just common sense that would have an effect on the climate. And that's before you even measure the number of parts per million in the atmosphere and see that it was within a consistent range for tens of millions of years or whatever. We can measure this from ice cores, and then all of a sudden now it's over 400 when it had been 300. So it's it's a small, I mean, it's a small molecule, but there's a lot of it that we've put into the atmosphere in 150 years. Has to do something.
Yeah, so I think that's an interesting point of view, but it sort of indicates that you're coming at it with like a frame of mind that is looking at like Earth as a mechanistic thing. I mean, what's sort of interesting, in my opinion, about climate change denial is the epistemic framework that people are working with who have that mindset, where it seems like they have extremely high epistemic standards for scientific knowledge, but extremely low epistemic standards for things that support their existing worldviews. And so how you work around that is challenging. Like, yeah, you looking at a picture of like CO2 over time as a scientist using ice cores or whatever, it's great. But if you Yeah, so I totally agree with you, and I think all that I would say to respond is that common sense is not common.
We have a question from someone who hasn't asked a question yet.
I don't think I can answer the question or ask a question about, explaining it to skeptics, but Brian brought up something about, it's not just the amount of carbon we're emitting, it's the fact that, all of you have mentioned, it's a complex problem, there's tipping points, and another part of the equation that's going on right now that, people tend to overlook is the fact that we're with all the deforestation, we're eliminating carbon sinks, and that also is adding into the equation. It's just super complex.
And really, something that I learned in my environmental science classes is that a good way to think about this is reservoirs and fluxes. So, maybe Newton can do this better because he's, but even if it seems like you're putting a lot of stuff into one reservoir, if the reservoir is super, super huge, then maybe it doesn't matter. But yeah, so I guess what you were trying to say is you have to look at things in terms of their relative fluxes and their relative reservoirs, and then that'll give you a sense of what's a lot and what's not a lot. Because, a bucket of water being dropped in the ocean is maybe nothing, but a bucket of water dropped on my head is a lot, so like it kind of matters. I guess, is that what you're trying to say, like looking at it more mechanistically? Yeah. Okay, cool. Okay. Awesome. Yeah, but it is a really complex system, and like systems thinking is getting to be more and more a part of environmental science curriculum, and because it's hard to think about systems, but that's kind of how we're trying to do it. We're trying to do it with fluxes and reservoirs, but then also zooming in and out on different scales. So I've talked a lot about macro energy systems, but there's also, to the level of devices that you have to do systems engineering for design, so, and then also zooming all the way out into the planetary science. And so basically sustainability happens on many, many different scales and in different applications. So it's a really complicated system, but a way to break it down is say like, okay, I'm asking this question, which scale am I talking about? Or which part of the big problem does this apply to, and kind of break it up like that.
Yeah. So another common, like, quote unquote, I don't want to call them skeptics anymore. Like climate denying folks usually say is that CO2 has been much higher before in geological time. Why does it matter now? And the answer to that is, again, it's a question of scale. Like, over the last 150 years, we've emitted as much CO2 as, let's say, during the PETM, which is like a mass extinction period, has emitted during that time for 150,000 years. So 250 years of CO2 emission compared to 150,000 years of CO2 emission. That makes a big difference. If I push you like really quickly, then you're going to fall. But if I like slowly just push you, you're not going to fall. You could fight back a little bit. You could respond. The system has time to respond. So it's really important to, again, understand the scales, which I think that a lot of modern science is actually starting to do, is understanding the interactions between different scales. I think what's basically like we're emerging out of this old approach where we approximated everything to like what we call spherical cows, like the simplest approximation, because now we know that these different nonlinear effects, these things that we would not assume as part of the spherical cow, would actually matter in the way that the system moves. Yeah.
In the process of putting carbon back into the ground, does the ground become saturated, or is like the Earth so receptive of it that it becomes an infinite size reservoir?
Yeah, that's a great question. So the main places that people are considering like putting CO2 back underground are actually places where we took the fossil fuels out. So the first place that people are going to is depleted oil and gas fields. And basically these, they're looking specifically at places where there are shale capping layers, so very, very fine grain sediments on top, and then basically it's porous underneath there. So then the gas is trapped in the pores and it kind of works like a liquid, and then the capping layer of the fine stuff keeps it there. And basically you can think about it like how it held the fossil fuels in there for how many years? Billions of years? Millions of years. Thank you for the right order of magnitude there. So it held the fossil fuel in there for millions of years. So basically we're just putting it back where it came from. But this is like a highly active area of research that someone at Stanford, who's one of my personal heroes, is Sally Benson. She's a geologist who works specifically on storing hydrogen underground, storing CO2 underground. Yeah, so hopefully that answered your question. But yeah. Mm-hmm. Yeah. So putting it back. Oh yeah. You asked, is there a finite amount of space that you can put the CO2 back into? Right? Was that your question? So the depleted. So transportation, what you also just said right now, is a problem. Currently, right now, you have how carbon capture and storage works is that you have a plant, and then you capture the CO2, and then you have to transport the CO2 to where you would store it, which costs money, But in addition to the depleted oil and gas fields, there are also things that people have stored gases in called salt caverns, CO2, and there's a lot of salt caverns. There's a lot of depleted oil and gas fields and aquifers. So there's definitely not infinite space. We have to also use wind and solar and other non-CO2 emitting sources of electricity, so we can't burn forever and ever and ever and assume that there will be space to capture all of it. But there is a lot of space right now that we could use, but not infinite space. Yeah. A volume, yeah. Right, no, definitely not. Yeah, so That's a great. Yeah, so some people are at Caltech actually are and your advisor are working on CO2 reduction, but you probably wouldn't want. So basically, you can take CO2 and make a fuel out of it, but because fuels are valuable, you probably wouldn't put that back underground. You would use it for plastic and other things, which you can maybe follow up on that after. But yes, CO2 has, as a gas, has much more, takes up much more space than a hydrocarbon fuel, which is like what gasoline is, which was the fossil fuel that was down there before. So, yeah. What's the relation of them? Yeah. Yeah. But a gas versus a solid. Oh yeah. Oh right. So then it's a fluid. Yeah, you put it in as a fluid. Oh yeah, I have heard. Wait, sorry, I missed that last part.
Yeah, I think this is sort of a complicated question because the phase diagram of CO2 is complicated. In particular, I think at high pressures you're going to depend. I'm not sure what the transition temperature is, but you're going to switch from a solid to a supercritical liquid, and I'm not sure what the density of that looks like compared to the density of, like, octane or any other common hydrocarbon. Yeah, it's a great question.
Presenting on carbon capture and storage underground, and the thing that he said when someone asked the question and said, but it's going to leak and then kill everyone when it comes out, is that he said that that was, I guess, a human problem, but it wasn't a geologic problem. So that basically, if you put it down in there and seal it with cement, then it won't leak, but I guess that I don't know. I can't remember what he said. You're shaking your head, but yeah.
So let's...
Right, yeah.
So we've just got time for a couple more questions, and I'd like to give the mic to somebody who hasn't asked a question yet. Yeah,
sorry about that. I don't know that much about the CO2 leaking, but exactly that. Right to say that there's things that are scary that we have to fix and worry about.
I would really like to know what the fanciest exoplanet is, or one of the fanciest.
Fanciest? What was that? No. If you got an answer, man, I'm ready to hear it. All right. Let's see. I think that there is a population of planets that are a few times the mass of the Earth and many times the radius of the Earth that effectively have densities similar to that of cotton candy, called superpuffs. I think those planets are really neat and are one of the biggest unsolved questions from the Kepler era right now is we just don't know what they're doing, how they formed, how they got there, how they've been able to retain such enormous atmospheres for so long. So yeah, I'm going to say cotton candy planets.
Okay, so with that, it's 9 o'clock, and let's thank our panelists again.